student here at the School of Earth and Space Exploration to introduce our speakers tonight.
Thank you. Good afternoon, everybody. Welcome to SpaceVision 2013. This talk's going to be called A Look into the Universe. And it is my pleasure to present to you our two speakers tonight. The first one's Dr. Rogier Windhorst. He research lies in astronomy, cosmology, galaxy formation, evolution, the cosmic dark ages, and the epoch of first light and astronomical instrumentation. Since the early 1990s, his group at ASU has contributed significantly to unraveling the formation and evolution of distant galaxies with the Hubble Space Telescope. He's one of the 6 interdisciplinary scientists for NASA's 6.5-meter James Webb Space Telescope, to be launched in 2013. Yeah, 2018. That's an optimistic version. His group at ASU plans to use JWST to map the epoch and the first light in detail. Our second speaker tonight is Dr. Paul Scowen. He works in development of next-generation detectors and instrumentation in his lab in this very building, the IST before, to enable new insights into star and planet formation, both in our own galaxy and in nearby galaxies. He works as the principal investigator on several space mission designs and concept studies, and is working hard to help NASA define what the future of space-based UV, optical, infrared astronomy should look like in the next 10 years. So give these guys a hand. And I'll turn it over to our first speaker here, Dr. Rogier Windhorst.
Okay, thank you very much, folks. So let's see. At some point, we'll want to switch off some lights. There's 3 reasons, actually 4 reasons to go to space. The most important for distant object view, the most important one, the skies out there in the red, near infrared, are 1,000 times darker than they are from the ground. In mid-infrared, they're 10,000 times darker. That turns this little telescope in the equivalent of a 64-meter ground-based telescope in terms of sensitivity, not in terms of resolution. Yeah, big advantage. Big. So we'll talk some about James Webb. That's what I do for a living these days. We launched precisely 4 years and 11 months. Is it not on? Oh, I had a red light earlier. How about now? No. Okay? Yeah. All right. And then if there's time left in the question and answer, I'll have some slides on this future ground-based telescopes to come after the CAC VLT. I also have some slides on future careers in NASA and a few other slides on supermassive black holes that, for the sake of time, I had to move to the spares. So just for the record, I was told that this talk cannot be longer than the length of an average Hubble exposure, 1,200 seconds. Yeah? So I'll get a warning, and then I'll skip. Yeah, thank you. All right, so very briefly, on the best of Hubble with the Wide Field Camera 3 that was launched last servicing mission, shuttle mission to Hubble in May 2009. And then measuring galaxy assembly, well, the spare charts was the supermassive black hole growth. Then the second half of the talk, what is the James Webb Space Telescope, brief bird's eye view. I have a whole hour talk on this that I gave here a month ago. I have another whole hour talk on lessons learned from this big project. How come we run over budget 2 years ago and how we got to be fine. But we won't get to that unless you have questions about it. I will have a few slides on this, how it can measure the epoch of first light, that sort of last major frontier before we get to the part where optical telescopes, infrared telescopes, can see nothing anymore because there were no stars. This dark ages, beautiful had few conclusions. Yeah, and as I said, this is my additional set of charts. My most important set of lessons is this one. We scientists all like to build a race car. We already have a blue race car, that would be the UV optical Hubble Space Telescope. Now we want to build an infrared race car, the James Webb Space Telescope. It's to make sure the thing launches on time and doesn't run on over budget again. We want to make sure we don't overload it, all right? At the same time, we don't want to de-scope it to the point that it becomes useless. So you need to walk a fine balance. If that's the only message you get from today, that would be a good one, yeah? So all of you will be building instrumentation for space exploration, currently or in the future. Keep this picture in mind. right? So the Hubble astronomer invented the expansion, discovered the expansion of the universe in the 1930s, after Einstein said it wouldn't be there. And then James Webb, the second NASA administrator, serving on the JFK, famous 50 years ago, and before, JFK said that we would go to the moon, and he actually didn't care so much about that as going to beating the Russians. And Mr. Webb said, no, Mr. President, to go to the moon, we not only have to beat the Russians, we want to make sure that we learn what's out there. So he invented space science. We're all here today because of Mr. Webb. That's why the Webb telescope is named after him. It's Hubble Sequel. Hubble itself was conceived in the 1970s, made in the 80s, launched in 1990. Spare parts to actually, turns out as of today, well into 2018. So it's a 30 to 40 year project, the length of a human career, right? Webb telescope, same thing, was actually conceived in the late 1990s, approved in the early 2000s, made this last decade, launched in October 2018, operational for a minimum of 5 years, propellant on board for 11 years. Yeah? Missions that last a human lifetime. Hubble Space Telescope, almost through scale here for the mirror, a little bigger than a human being. James Webb Space Telescope mirror, 2.5 times larger. So at the same wavelength, you get 2.5 times better resolution, Orlando, this thing than Hubble. And at longer wavelengths, of course, you get the same resolution as Hubble. So it's the infrared sequel to Hubble. The Hubble Wide Field Camera 3 was installed by the shuttle astronauts, replacing the good old Wide Field Camera 2 that Paul Scowen will talk about. That was an absolutely gorgeous instrument, operated for 16 years, done beautiful things. And then we had one last chance in 2009 to replace that by the Wide Field 3. Here it is. It actually was made out of parts from the good old Wide Field Camera 1, so we knew it would fit, flown in the telescope for at least 3.5 years. It came back. You see the outer shield has a good bit of 3.5 years worth of micrometeorite hits on the outer titanium. None of them catastrophic. They're very tiny, very much sub-millimeter size, but they're in the shield. It's also relevant for the James Webb Space Telescope. Timescale of 10 years, you get hit by little things. Completely revamped, completely new set of infrared detectors, best optical CCDs, best filters, replacing the Wide Field Camera 2. You probably know the rest is history. I'll spare you all the details, but sensitivity roughly from 0.2 microns, 2000 angstroms, to almost 2 microns here. There's the infrared channel, much better than the previous generation. Here's the optical UV channel, much better than the previous generation, except for the advanced camera, which is more sensitive, but over a very limited wavelength range. So with 10 filters from the near UV to the near IR, you can sample any kind of galaxy, whether it's a late-type star-forming galaxy with almost a flat spectrum, this is the spectrum versus wavelength, or an older galaxy like an elliptical, or many old stars, which has less light in the UV, more light in the red. And then, of course, due to the cosmic expansion, the universe gets bigger, we look further back in time, the light gets stretched or redshifted, and therefore any of these galaxy spectra gets shifted from the blue to the red. This filter set is perfect to do that over a field of view of a few arc minutes. And James Webb, very much the same, except it will add another factor of 10 in wavelength theory, more than that. So this is the 30 Doradus Nebula, not in our own galaxy. It's a star-forming cluster in the Large Magellanic Cloud. Very young, hot blue stars. We call these the cosmic fraternity members. They live fast and they die young. Right? This is in the optical, this is in the infrared, this is much what James Webb will see, except that Webb will penetrate further into the dust and the smoke further into the infrared at much fainter levels. It is these young, short-living hot stars that make stars like the sun in pillars of creation like this. This is one in the Large Magellanic Cloud, where the radiation pressure from this enormously hot star cluster sculpts away. You see it in the infrared at the end of this finger. There's actually a little star right there, there's actually more than one, like the sun forming. So stars like the sun form in the aftermath of the cosmic fraternity members, and Paul will talk more about it. Yeah? You can see this also in nearby galaxies. This is the nearby galaxy, only 4 million or so light years away. M83, this is the core, supermassive black hole inside somewhere. The red hydrogen gas following the spiral arms, the blue hot star-forming UV light from the cosmic fraternity members, especially these star-forming clusters here. Beautiful congregation of stars, about 100 billion of them in the entire galaxy, and the sun, if this were our own galaxy, would be in one of these spiral arms, about 100,000 light years from the center. So Hubble has done amazing things here. This is Stephan's quintet, another a group of galaxies, older galaxies. This will be one like our own, but at a distance of about 20 to 30 million light years. This one's actually the foreground. These other four are colliding. Colliding galaxies is, like cosmic mergers on the cosmic stock market. Is very common, not so much in today's universe, but back in the early universe, all these tiny building blocks would, under influence of their own gravity, gobble each other up and grow bigger galaxies over time. Yeah, and while they do that, they form these beautiful star-forming rings and arms along the spiral structure, and they use up their remainder gas to eventually become something old and red and dead, which is this elliptical galaxy here. Hubble had discovered this in great deal, starting in the 1990s. This is one of the medium deep fields. It's not the ultra deep field. We'll get to that in a minute. But it's panchromatic. It stretches the entire visible spectrum from the near UV to the near IR. These are foreground galaxies, relatively foreground galactic backyard, we say about 1 billion light years away. And these are galaxies that are visible halfway between us and the edge of the visible universe. They're about a redshift of 1 when the universe was twice as small as today and only 6 or 7 billion years old. The average level you look down to here for astronomers is in magnitudes. That's the equivalent of about 100 fireflies as seen from the moon. Over a relatively small angle. Remember that Hubble has a small field of view, so it's like looking at the universe through a straw. You see a very tiny field, and inside that field there's tens of thousands of galaxies. All of these things here, with the exception of things like that's a galactic star or a fly in the windshield, if you wish. Everything else is distant city lights on behind the highway roads of distant galaxies. So only that is a star in our own galaxy. Yeah? Every galaxy contains on average about 100 billion stars. I used to be able to say in my talks that there will be about as many stars in each galaxy as there were dollars in our national deficit. That's not the case anymore. Galaxies don't grow that fast. But you got the point. Each one of these is about 100,000 light years grown. Now, further away, these galaxies actually are smaller. They haven't grown as much. They're not only smaller because they're further away. If I take this stick, 1 meter in length, and put it twice as far away, it looks twice as small, right? We call that the small angle approximation in a math class. If I put this stick at a radical 1, which is a minimum angular size, and push it further back from you, actually grows in size. It's a cosmological geometry effect, very tricky. Makes the galaxies actually larger in the sky at smaller distances. Yet they are actually smaller because they hadn't grown as much. So the further you look back in time, the smaller the galaxies are because they hadn't grown as much. The Webb telescope will look, about 100 times fainter to the level of about 1 firefly as seen from the moon. We'll see this much further into the infrared, including where behind the dust, like you saw in the case of the cosmic fraternity members, all the young hot stars form and grow. Yeah, and evolve. So this is the James Webb Space Telescope, 25 square meters collecting area, 6.5 meter edge to edge. This is the 5-layer Kapton sun shield. So these are not the solar panels. That's not the solar panels either. They're over here. That produces power. These are radiators and other devices to use the high gain antenna here. It works from visual to 28 microns in wavelength to be launched about 5 years from now. Right, and this nested array of sun shields keep the temperature, the ambient temperature. The sun is always on this side. Keeps the temperature here always less than 40 Kelvin. Of course, you have to always steer it away from the sun and the Earth and the moon. You would actually launch it, in this case on an Ariane 5. It sits folded up with, the sun shield and some of the mirror panels folded backwards in the launch fairing of the Ariane 5, weighing less than 6,500 kilograms, and then get launched from Earth, past the orbit of the moon, into the gravitational Lagrange landscape. So if the sun is over there, 100 times further away than the moon, we're here, there's the moon. We're 5 times further away than the moon, here in the L2 Lagrange. Yeah? You describe a vertical and horizontal orbit. They're sort of like a listed view figure. It's not a stable orbit. It's very dark. There's no moon, earth, and sun. It's all behind the sun shield, so it gets very, very cold. Yeah? It's a perfect environment for an infrared telescope. In fact, the only logical place you should put an infrared telescope. Hubble, very traumatic. Also for the astronauts. 96-minute orbit. 16 sunrises, 16 sunsets a day. Lots of temperature difference between 100 degrees centigrade and minus 100 every 96 minutes, 16 times a day. When Hubble is done, hopefully in 5 years or more, we'll have had more than 150,000 sunrises and sunsets. This telescope, over 11 years, will have one sunrise when it gets outside the atmosphere, and one sunset over here when the sun's shield before. For the rest, it will always be in the dark. So an enormous difference. All the hardware is being built. Mirrors are all made. Primary mirrors, all 18. Secondary mirrors, tertiary mirrors. The support structure, the bars that bring the secondary mirror down, I'll spare you all the details. The giant tennis court sun shield, bigger than this room, almost twice this room. The spacecraft electronics and all the other structures. 80% built. In fact, they should all be green check marks. All mirrors are now made. Here's the entire family portrait, including the secondary, tertiary, fine steering. So the whole optics is done. It's now all being assembled. Yeah, here's the near-infrared camera built by the U of A. It was delivered in September. Here's the fine Geiger sensor made by the Canadians, delivered in last year. There's also a European spectrograph, the NIRSpec, and a European mid-infrared instrument, also delivered in NASA, either last year or this last month. So all 4 instruments are now in the possession of Goddard Space Flight Center, which you can see here. This is building 29. And that's where they are being assembled into the ISIN, the instrument module, which is the thing that sits behind the telescope here, where all the instruments are put together and being tested. So right now we're in the stage that everything is being put together. Secondary mirror support structure with a tripod, the baffle here, the primary mirror support structure from carbon fiber, the instrument module here with the 4 instruments, the spacecraft electronics, everything down here, including the sun shield, not showing you how we're doing in time there. 5 minutes. Yeah, 5 minutes, so we're doing good time. And so the point is that you know, the spacecraft is 80% done. We still have 4 years to go before, you know, all the final testing is done. In fact, to test something this complicated, remember, L2 is a 2-month journey. You can't just go to this place over here and send an astronaut. Well, you could, but you know, it's a 2-month journey. It's not without danger. To service it, you can also not easily bring it back to service it around, let's say, the space station. So you have to make sure it works 100% here. So there's a lot of spare parts, a lot of redundancy, a lot of testing is being done, and all of this hardware is now being tested in, that will be happening late 2014, 2015, early 2016, in the largest thermal vacuum chamber in the world here. This thing is over 50 years old. It was actually built by James Webb himself. This is the size of a human being, a 20-meter door here. Inside this tank fitted the entire Apollo moon lander and capsule, not the whole Saturn V, but in the 1960s when the Apollo missions were built, the entire thing that went to the moon, including the lander and the third stage, were in here in the thermal vacuum testing. So this entire chamber is now being refurbished so that in a year from now, the entire telescope will sit at the bottom, door closed, technicians taken out, pumped vacuum, and brought down to 40 Kelvin. So that in one gravity, we can test whether the whole thing works. We can test with this optical test tower to make sure that underneath every one of these mirror segments, the hexapods can actually precisely push, pull, tip, tilt, rotate, translate 7 degrees of freedom with a lot of internal redundancy, push any one of these segments perfectly into place. So we don't run into the issue that Hubble had, star collaboration, flaws in its mirror. We know A, that we don't have those flaws. Those mirrors are made nearly perfectly. B, even if we had some of those flaws, we have a lot of redundancy to push it out. And this test tower, this entire test chamber, will test that in 2015, 2016. Yeah, so when that's all done, there's a room, budget, schedule allowed for a second test. Each of these tests last half a year. 2 months to cool down, 2 months to do the test, 2 months to warm up, very roughly. Right? If something breaks, you wait until the end, you fix it, and you do it again. Hopefully you don't have to do it more than twice. Yeah? So you better make sure everything works when you close the tank and test it. In any case, so very last, on what will this telescope actually see? One of the most beautiful images here of Hubble, I think, is this giant cluster of galaxies. This is now like the Los Angeles greater metropolitan area. LA, Pasadena, all the suburbs here. Every galaxy is a suburb. Every suburb contains 100 billion homes on scale. This is so much mass, of the order of 10 to the 16 solar masses, that a background galaxy, the background galaxy, which is now halfway seen between us and the universe of our radius of 0.7, maybe 5 billion years back in time. The galaxy here in the background will actually not be seen right here, but will be gravitationally lensed like an arc seen over here and there and there. It's a little bit like looking at the universe through an empty glass Coke bottle. If I look at that lamp with a glass Coke bottle that's empty, I see a ring. Gravity does exactly the same thing for you. Yeah? And that's what we think we'll see a lot with the James Webb Space Telescope, because further in the infrared, the most distant galaxies at redshift 10 or 20, with the universe 10 or 20 times smaller than today, it was only of the order of 500 to 300 million years old. These galaxies will be sitting behind these foreground objects and will gravitationally lens into the images. So keep that in mind, gravitational lensing. Last chart, these Hubble images, this is the deepest image ever taken from the blue to the near IR. 522 hours of observing time spread over several years. All these foreground galaxies will, to some extent, also start lensing the background galaxies, because these green circles are galaxies seen in the first 600 or 700 million years. The yellow circles are seen in the first 500 million years, and that one is seen in the first 400 million years. This is sort of the very limit. This is now the brightness, this little red thing in that circle. That's the brightness of one firefly as seen from the moon. It takes Hubble 522 hours. Will take the James Webb Space Telescope about 24 hours. Of course, if the Webb telescope is going to point at the same field or a different field for 1,000 hours, the image will get so dense that the galaxies will start overlapping. So I'll send you away with this last chart here. We'll have two effects. You can't see the forest for the trees effects. The images will get so dense that galaxies will start overlapping in their rings. Like if every tree in the forest was a simple delta function with infinitely narrow width, I could look through the forest, but that's not the case. The trees have their own finite width, and they will start overlapping in the image. That's just a numerical mathematical effect, a nuisance in the data reduction. In addition to that, you get the House of Mirrors effect, the gravitational lensing, that there's so many foreground objects that when you look for the distant background objects, they're not seen by you, fellow in the back, along a straight line of sight. I don't receive your light straight from you to my eye. No, your light will be gravitationally lensed by all these thin people in the foreground and come to my eyes via two curved paths, right? Like you saw in the case of these arcs. So the universe gets very contrived, will be very dense, and there will be lots of lensing when Webb first shows its images. So, just to summarize, Hubble set the stage to galaxy formation. Webb is now well on track after it run over in 2011, more than 80% of the hardware built. We're now in the process of integration and testing. We will measure that apple in first light. The first proposals are due less than 4 years from now. And for the young audience here, I think most importantly, this infrared sequel to Hubble after 2018, we will be using it to train the next generation of researchers and explorers like yourself, and we'll also set the stage for the next frontier, which is the cosmic dark ages. Yeah, how we're doing that? Yeah, all right, Paul's turn, and I'll be happy to take your questions.
All right. Okay, so Roger told you about what has been going on what is very soon to be coming online in terms of what our view of the universe is very soon to be like. What I'm going to be talking to you about today is what's going to be happening after JW or at the same time as JW, but that is in its earlier stages of development. The first thing that we need to look at is a brief discussion about how does this all come together? How do we figure out what the next important science is going to be? Astronomy and astrophysics, like many other physical sciences, has a mechanism by which they look at what is the hot science right now. They take all kinds of input from the community and they figure out what those next 10 years are going to be like. Those are called decadal surveys. They are run by the National Academy, and they come out every 10 years and tell you this is going to be the next hotness, and that's what all the various funding agencies, the NASAs, the NSFs, the DOEs, that's what they take as their marching orders and their prioritization. And so if you are in the business of developing what the next generation of science, what the next generation of technology is going to be, you need to be seen to be aligned with that to understand what you're going to be allowed to be funded to do. So the next few goals that are going to come, that have been laid out by the Decadal Survey on Astronomy and Astrophysics that came out in 2010. The first of them was the idea of targeting cosmic dawn. Now, Roger already talked about this some, presented some spectacular data. And this is a mugshot sequence here of objects that are right at the hairy edge of the visible universe. And not too surprisingly, they're fuzzy blobs because it's awfully difficult to see what's going on out there. But there's a variety of different techniques, spectroscopically as well as imaging, that you can use to target those first stars. Because think about what you're trying to look at there. You're looking at the first time large clouds of hydrogen gas were aggregated together to make stars. In the absence of heavier elements, in the absence of dust, all of this stuff was a totally new environment for making stars. Very different from what we consider to be common or garden approach that we see in nearby galaxies. And this was when the first era of the most massive stars formed the first candidates for black holes. And did those then play a role for aggregation and construction of galaxies around them from then on? So that's one area that is of dramatic interest. The other, of course, which is very, very hot these days, is the business of exoplanets. In just 10 years, we have gone from a rather idiosyncratic science where people, we just caught one planet transiting across the face of this particular star, and we've gone into this era with Kepler where we have found truckloads of these things. We find, not too surprisingly from the approach that Kepler took, we found very large planets very close in to their stars because the orbital period, the frequency with which they're going to go zipping around in front of the stars, it's easier to see those first, right? You have to look longer to find the ones that have longer periods that are going to be harder to find. But this is really a very important, very high priority science or discipline that people are wanting to invest a lot of time and money in. And so that is another one of the areas. And the other came out of work that has been done originally with things like balloon experiments, and then subsequently with a mission like WMAP that went out to L2, and started to look at the overall structure of the universe as we can see it. And to look out there, this is the WMAP 7 map of the sky, and to look at all of the fine-scale structure that you see in there, and what does it tell you about the frequency with which different modes appear in the large-scale structure that you see within the universe. And when they did that kind of an analysis, they ended up with this now rather famous power spectrum of angular size versus temperature fluctuations. And the majority of these bumps that are in here, at some level were expected, but the relative sizes of them and the widths of them laid down some restrictions on things like the Hubble constant, which gives you the overall sense of scale of the universe, but also the distribution of energy and matter between different phases. And it was with a certain amount of surprise that when they did this head count, they came up with this rather famous distribution that we are now trying to come to grips with, that the part of the universe that we inhabit is rather an afterthought by comparison with the rest of the known universe. That there's an awful lot of energy and there's an awful lot of material that we simply can't see because it doesn't interact in a very straightforward way with the baryonic matter that you and I see each and every day that we are made of. And that, understanding that sequence of events and how the physics behind that works, it has been deemed to be a very important way of getting there. So, looking at some of those facets, Kepler we of course have been very used to. Kepler studied it, pointed at a very particular part of the night sky in Cygnus and looked for as many stars that blinked as it could find in its mission lifetime. Unfortunately, Kepler is now unable to do that kind of science. NASA is looking into different ways to use it for other kinds of science because it had some of its reaction wheels fail. But it has been a remarkably successful mission. And what do we do now that it's toast? How do we continue that project of trying to find more stars and planets out there? Well, the Kepler Second Science Conference was this past week, and this was the tally that was reported in terms of Earth-sized planets, in terms of super-Earths, Neptune size and Jupiter size. And that is a remarkable number of planets that have been found in just that particular part of our particular galaxy. And it is a very large number and does imply that just about every star you look at in the night sky probably has some kind of planet around it. Whether it's Earth size is a different matter altogether. So the future of this endeavor right now is characterized by this particular mission, which is an Explorer that was selected last year. This is TESS. And TESS is a much more modest affair than Kepler was, and it is going to be capable of looking at many bright stars and finding, as a result of that, probably a lot of planets around those bright stars because it has a much more modest technical capability. However, one of the things it's got to come to terms with is the size of the hole, the size of the dark spot that goes across the star. For instance, we have found an awful lot of planets associated with rather faint M-dwarf type stars because the percentage, that planet represented a larger chunk of the size of the disk, so it was easy to detect. With these brighter stars, it's going to be a brighter, bigger disk, and so the size of the effect will be less marked. But since the number of photons you're getting per second from those bright stars is higher, the statistics work in your favor, and you should still be able to see a measurable signal. So this is what, in the short term, probably over the next 3 to 4 years, is going to pick up where Kepler left off. And it's going to be doing it across as much of the sky as possible, rather than just this little postage stamp up in the constellation of Cygnus that Kepler's been using. The other aspects of the decadal survey were addressed by the decadal putting together a mission concept that used a variety of different inputs that were given to it, and they saw a lot of commonalities between them, and so they came up with a mission design for us called WFIRST. And this used, as you can tell from the name here, it's a wide field imager that does surveying work in the infrared. And an awful lot of the science goals that were deemed to be very highly important by the decadal were seen to be met by something like WFIRST, and I'll talk to you about that in a minute. And I'm also going to throw in a plug for HORUS, which is the mission that I'm the PI on, which also fulfills a large part of the origin science that comes out of the decadal and has an opportunity to make that happen in relatively short order should the powers that be decide they're going to do it. Because, and this is colouring both WFIRST and HORUS, a number of years ago here, the National Security, or the National Reconnaissance Office, actually NRO, not NSO, excuse me, NRO had 2 spy satellites that had been sitting in storage up in Rochester, New York, and suddenly said, we don't want to keep these anymore. And so they gave them to NASA, and NASA has been collectively wringing its hands in the intervening 2 years, trying to figure out what it's going to do with them. It has, at this particular juncture, agreed to consider using one of them for WFIRST, because you're essentially getting a free telescope. And it hasn't figured out what it's going to do with the second, and I'm trying to influence them to use the second for something like HORUS. But this is an opportunity. It's not a free mission. The telescope part of any mission cost really only represents about 20% of the cost, but it is enough of a freebie that people in Congress are willing to listen to arguments as to why it's a good idea to use it. So, WFIRST itself is, as I said, a wide field infrared imaging survey telescope. Roger had mentioned about how both HST and James Webb have relatively small fields of view, but exquisite resolutions to take advantage of the aperture that it provides. However, if you're looking for things that you don't know exactly where they are, a survey-based system like this is really the approach that you need to take. And that is why it has been designed around that, using these large format infrared detectors and tessellating a whole stack of them together to give you that kind of capability. So WFIRST is supposed to give a complete census of planetary systems in our galaxy, because with this kind of field of view it can do it. If you try to do that with James Webb or with Hubble, you couldn't do it. There's just not enough hours in the day during the mission to be able to do that. But the idea is to go after as much of the population as possible to find outer habitable zone free-floating planets and all kinds of smaller mass planets that the system would be sensitive to. The larger issues of the overall scale of the universe, to understand how dark matter plays a role and dark energy, is to use a variety of different techniques that were being essentially competed against each other before the decadal survey happened, but have now been forced to play together. And that uses things like looking at redshift surveys, doing a supernova survey over large ranges of galactic age, and to look for gravitational weak lensing surveys. All of these are probes that allow you to look at how the expansion rate of the universe has changed over the course of its history, because they can be used to put down little markers all the way back through the course of time, because as you look out through the universe, you are looking back in time as you go to further and further redshift. And the idea is to look for departures from the expected structure and expansion of the universe, and to look for where those discrepancies might be, as they may correspond to departures from what we would understand general relativity to predict. Because it is the nature of how dark matter and dark energy interacts, however weakly, with the baryonic matter that we can observe. That is the so-called smoking gun that will allow us to maybe try and figure out what the nature of and the distribution of that dark material might be. Another thing that it wants to do is also to produce a deep map of the sky at near-infrared wavelengths, to map the galactic frame, but also to go all the way back to mapping the impact of the reionization epoch by finding quasars at very high redshift. And again, you need a very wide field of view to be able to do that kind of thing. So the dark energy roadmap, and I pretty much talked about this in rather cursory notes, but the idea is to go with different approaches, looking at weak lensing, to look at galaxy redshifts, look at supernovae. All of them give independent but relatively commensurate evidence that allows you to track where dark matter might be. This is an example of a massive cluster that is lensing light. This is very similar to the exquisite pictures that Roger already put up. But some of these are very big on the sky, and for you to be able to measure all of the redshifts and stuff that you need a wide field of view. And you can't do that with Hubble, and you won't be able to do that with James Webb. That's why this approach has got to be taken. And looking at lenses, stars being lensed by foreground stars that might have planets going around them, you will see in the temporal regime, you'll see occasional blips, and these blips will come from planets orbiting around those stars. It's a little less direct than the direct obscuration of the star, but it is a very sensitive technique and will allow us to look at planets in a much broader swath of the galaxy than we've been able to do up to now. So I'll throw in a few words here about HORUS. HORUS is a wide field, another wide field survey instrument. UV optical globe, not infrared, because there's a variety of different spectroscopic diagnostics in the ultraviolet and a variety of different optical band science that we still need to do. It is a 2.4 meter class, just like WFIRST is, and again predicated on the availability of these free mirrors. But the design provides a 1/4 degree wide field of view, but it's a dual channel imager. It's a red and blue imager that shoots both channels at the same time, so you're not throwing any light away. But it also combines it with a next generation far ultraviolet spectrograph built on the Cosmic Origins design, but the next generation invocation of it that is flown on HST right now. The point of this approach is to allow discovery from the wide field of view, but also to preserve the very limited, the diffraction limited resolution of the system and allow you to characterize objects once you find them. So the kinds of science that we're going to go after, and you'll notice that this is essentially the optics that you saw in that earlier picture with our hardware bolted on behind it, and this is how big our field of view is. But it's to go after a broad and narrowband imaging census of all the high mass star forming sites within 2.5 kiloparsecs of the sun to produce a statistical insight into this process. We've done fantastic work looking at this little object over here, this little object over here. We haven't looked at the ensemble. And that is what step 1 is all about. Step 2 goes out to the Magellanic Clouds. Roger already showed you a picture of 30 Doradus. That is the nearest example of a starburst class star-forming event. And then to go out beyond that into star formation regimes in nearby galaxies where the metallicity changes, where there are collisions between galaxies that change the way star formation works, to just look at the range of possible nodes, and ultimately to look way out into the universe, to look at star formation and metal production rates in the distant universe. Once you get out that far in redshift, you're then treading on JW's toes, right? That transition from optical to infrared, that there's a line in the sand that we will be able to go up to, but JW is built better. It has been designed specifically to do that kind of work better than we can. But there is still a contribution that we can make. So a brief aside, talking about the star formation in our backyard, you're familiar with this picture. The reason that we took this picture back in the day with the WFIRST 2 on HST, which was the first corrected camera on the observatory, the reason we took this picture was to look at how narrow that edge is, because that represents the transition between this dense clouds of gas and dust and the ionized volume of this cluster. At this rate, about 2 stories above here are a bunch of very massive stars, those live fast, die young things that Roger was talking about. They're the ones that kick out enough ultraviolet flux to light up the neighborhood in the way you see right here. But they also kick out a lot of strong stellar winds. So the material on the top of these columns gets heated up and then ablated away by the strong stellar winds. So it's an erosionary process. And the reason that these pillars are aligned the way they are is that the material in between has been blasted away. And what's protected these? Well, at the top of each of these columns is a much denser cloud of stuff that is protecting or shadowing the columns underneath. And that's why the pillars are formed in the way they are. They're very big. This is 3 light years from top to bottom here. So it's a large amount of real estate. And each of these little blobs that you see up at the top here being dug up are new stellar systems with some planetary systems forming around them that are being dug up by this erosionary process. But what this represents then is the system is getting messed up, right? These are new stars that are forming in the area around where you've already had a bunch of stars form in the first place. These stars can no longer get as big as they would have because they're being dug up from the cocoon, the source of material that is going to be aggregating into stars, before they're ready to do so. And so in this one photo, this represents the impact of what is called secondary star formation on the fact that it is right next door to a primary star formation event. Now, the really interesting thing is when you go from this, which is an optical picture, to the infrared, and you see how much is going on inside these pillars. And that's how many stars are buried in the back wall of the nebula and in the pillars themselves. You can see down here in the heart of this one here, there's a really very bright, very massive star that is still trying to form. It hasn't been dug up yet, and it's going to be liberated soon. This one you can see is right at the very tippy top of the column, and there's a hint that there's maybe something starting to break out there. But ultimately, it is the combination of both the optical and the infrared that allows you the insight into the star formation process. And so it is the commensurate nature of what JW will bring compared to the wide field optical capability that the Horus could provide that would allow you the kind of insight that we believe you're going to need. This is the Carina Nebula. This is a mosaic that was produced by the Hubble Space Telescope by our good friend Nathan Miller down in Tucson. Nathan Smith. And what this is a mosaic of as many as 50 different pointings with the Hubble to produce this spectacular image. The wide field impact that Horus could bring is that it could take this entire picture at one snap. It has that ability with the angular field of view and with the right filters in the camera to be able to do the whole thing in one go. And what you see when you get right down into this, and this is an illustration of why you need both the wide field of view but also the exquisite diffraction limited resolution that a 2.4 meter or greater mirror will give you, is that when you start looking at the different blobs, little bits and bobs in here, you start to see spectacular structure. Wrong way, excuse me. Where you start to see stuff that is broken off from the wall of the nebula and is being photoablated away in exactly the same way that the Eagle Nebula, the Pillars of Creation, was doing. And down inside these, in exactly the same way that we saw with the Eagle Nebula, there are new stars forming in these broken off clumps. And the question is, how much does this breaking off, this erosionary process, impact the next generation of star formation? And why do we look at this as intimately as we are? Because this is where we come from. When you look at the meteoritic evidence that we find in our own solar system, in the collection we have upstairs here, there are different isotopic ratios for things like nickel and iron that betray the fact that our own solar nebula, when it was in its earliest of stages of formation, was exposed to a nearby supernova. And the only way you can get that happen at that particular point in the formation, statistically speaking, is that it formed in a massive cluster like this, where you've got that many massive stars, because it's the massive stars that go supernova, and you've got them in that closer proximity that one of them goes foom while you're still in the process of forming. So we're looking at our roots. This is where we came from based on evidence we have found in our own solar system. So to finish up, Where are we going? Exoplanet discovery has been very, very hot, very sexy, and that is going to continue as we move forward from Kepler using things like TESS. JW is very well built to do this kind of work, but it has a small field of view, so it needs different projects to work together. And WFIRST is going to be contributing to that as well. One thing I didn't talk about is that WFIRST has deliberately pieces in its design to use LEO-type coronagraphs or the potential for an external occulter to actually go after imaging of exoplanets. And so exoplanet imaging is coming by one of those two methods. The nature of dark energy and dark matter is a very high priority issue for the agencies. WFIRST is being built around going after that. There's going to be programs that JW will do as well as that. And we have ground-based facilities like the Dark Energy Camera in Chile and other facilities that are trying to do the kinds of observations necessary to understand what's going on. Astronomy in general, you may have seen from some of what I'm talking about here, is heading in the direction of wide field survey-based facilities now. We've had fantastic work with very small fields of view, but we are now getting into modes with a lot of the science we want to do where you have to get into discovery spaces that involve large angular extents on the sky. And so a lot of things like ground-based LSST, WFIRST, and our Horus design have been built around that deliberately. We need both the combination of a wide field and the highest of resolution to be able to do that. And with that, I'll leave it and we'll address questions. Thank you.
All right, everybody, so if you have a question, just raise your hand and I'll come over and give you the mic.
Who wants to go?
I'll try to run as fast as I can.
Tell us first what your topic is so we can put up the right slide.
I have a question on the James Webb telescope. When I was looking through your slides, I noticed that a lot of the components are made by different companies.
Yes.
So you contract it out. So if you're interested, or if someone's interested in going into the field of space telescope, where would be the best place to go for that?
Okay, so your question is, with all these companies involved, let me go get to the chart that I have in my extended talk here where it shows all the companies involved across the U.S. There's 27 U.S. states and it's full screen. And more than 10 countries in Europe plus Canada involved in this. So if you want, rephrase your questions. Tell me the second part. Make sure you answer it correctly.
Just wondering, where would be the best place or company or organization to get involved with if you want to do space telescope?
I can get you a copy of the chart if your conference organization be so kind to put all these on the SEDS website. My extended version of the talk has all this in there. There's also in my actual talk of today a link to this extended version. So all the companies are listed here. There are too many to mention. Northrop Grumman is a good one. Let me give you a very specific answer. Roger Rouse, one of my ex-grad students that worked with Dave Burstein and myself, is here. He works for Lockheed. Lockheed built Hubble in the 1980s, right? So talk to Roger before you weigh out. Is there any Northrop folks in the audience? Talk to the folks at Northrop, Boeing. They've all been involved, the big three, in making Hubble. Northrop is taking the lead on the James Webb Space Telescope. There's companies here in Arizona, like Raytheon near Tucson, that builds the mid-infrared detectors. There's Teledyne and Rockwell out in Thousand Oaks in California that builds the near-infrared detectors, also for White Camera 3. There's too many to mention. Yep. So you don't have to move states. You can work right here. Just find the right company and tell them you want to build the next James Webb. I hope that helps. Yeah? Next question.
Yes, thank you for that presentation. It's a great look at what lies ahead. For full disclosure, I retired from NASA as the program executive on the Discovery program that selected the Kepler mission. But another project I was intimately involved with at NASA for many years was the SOFIA 747 Airborne Infrared Observatory. And I wonder if you could comment if, from your perspective, and I'm not very familiar with the instrumentation that currently exists with SOFIA, how it might contribute to some of the investigations or goals that you've laid out for these other missions.
The universe is a complex thing, right? The university is also a complex agency. We have a physics department, we've got a chemistry department, it has the physics department. It's a long answer to your question. SOFIA is built to do the chemistry of the universe, right? Hubble is the atomic physics. I won't get much of the chemistry. In the UV optical, you study the atoms, especially at a higher redshift where you look far back into UV. You won't get to the chemistry. In the near infrared, you get a little bit of chemistry like OH, carbon monoxide, carbon dioxide, ozone, the atmospheres of exoplanets, James Webb. In the far infrared, what SOFIA is perfect for, you get to the real chemistry of the universe. And so, and I didn't talk about that, but it's a perfect example of how big the universe is, how much the electromagnetic radiation is spread out over 20 orders of magnitude from gamma rays to radio waves. And SOFIA is built to fly above the atmosphere. It's a 747 with, is it 2.5 or 2.4 meter telescope, just like Hubble. And it sits above the atmosphere, most of the atmosphere, 45,000 feet or something like that, where we're above most of the nuisance from the oxygen in the OH. And you can actually, begin to see the markers of star formation at these longer wavelengths that you couldn't begin to do from the ground. Right? For the same reason that the sky in low Earth orbit in L2 is 1,000 or 10,000 times fainter than it is here on the ground. It is the oxygen and the OH in the atmosphere that prevents you from looking at these things in the galaxy. But the 747 with SOFIA's telescope can actually do that. But that's at longer wavelengths, and of course in a much more steady way than James Webb can do. Is that a good
20-some years of operation.
That also, yeah.
With instrumentation that you can improve on.
So it's a very different and very complementary way of doing business. You build a telescope, you can keep updating, keep flying. The 747 can fly for 30 years. And James Webb, of course, because of its propellant, has a finite life. Good point.
Hi. So with the picture, the beautiful images that we've seen from Hubble and such, a few of the images that we saw were some of the, I guess, most distant or earliest and furthest we could see that appeared just as basic blobs to us. With James Webb, or the telescopes that we're going forward with now, being able to see further, will we have Hubble-like images of those first formations, early galaxies and stuff?
Yes, we will. As I showed in some of my first slides, so James Webb is 2.5, 3 times larger than Hubble. It's not around here, so it is between that range. And so at the same wavelength, it will have 2.5, 3 times the resolution that Hubble does. So an image like this, everything will look 3 times smaller and broken up. Now, the galaxies are already resolved, but a blob like that may actually start breaking up like something like this or that. At the longer wavelengths, you get the same resolution as Hubble, which is a really good thing. And of course, if you want to take the next step and get, say, 3 or 5 times better than James Webb, then you'd have to use the large ground-based telescopes that are currently on the drawing boards at 20, 30, 40 meters. Because they have one advantage that Hubble and Webb don't have. They have a much larger real estate, so they can get better resolution. But they won't get it over a panoramic field like this. They will just take a small postage stamp and zoom it up by a factor of 5. So again, it's like SOFIA, they're complementary to what Hubble and Webb do.
So you have time for about 2 more questions, so I think you had your hand raised. Which agency is HORUS being developed by?
It's not being built by anybody yet, but
It's private funding?
No, well, right now we are proposing to NASA, and we went and had a big presentation at Marshall earlier this year, when NASA was still in the mood to discuss what was going to happen with the second of those mirror sets. Then the sequester happened, and they all suddenly got cold feet, right? We came out of that smelling like roses. Our project was the best designed, most mature, met the biggest science portfolio. We've just done a variety of different surveys with the community, and we found that when you ask the community what kind of science, irrespective of cost or capability, do you want to do over the next 10 years, that Horus fulfilled nearly more than 2/3 of that kind of capability with the science and the technology that we were willing to put together. To answer your question, yes, we are looking at private solutions to make that happen still, because the assets are still there. It is NASA who's just got the cold feet about making it happen.
There's another question over there.
Hi, my question is about coronography, and I was just wondering if you could maybe talk about it a little bit, and also, do we have a way to detect magnetic fields of distant planets?
Magnetic fields of planets. Okay, coronography itself, this is a technique that's been around for a while, right? Basically, the idea is to stick your thumb up and put it in the way of the bright star that's getting in the way. There you go, that's coronography right there. There's a variety of different ways that you can tackle this particular problem. This is just a simple mask coronography technique, and you can see that light will spill around it, it will scatter around the central obscuration you put into place, because that's the first order, simplest way to do it, right? There's another technique which I mentioned called a LEO approach, where you're actually working in the Fourier domain, where you use the diffraction of light through an optical system, you can use the laws of Fourier optics to get access to the image pupils in the course of the optical system. And if you put in coronography stops like the one we just looked at there, but not in the direct imaging plane, but in the corresponding pupil planes, you can actually block out the light in a very easy way, and it throws away the majority of the light without any kind of obscuration for anything that's a little bit off axis. And there's a variety of different approaches that are being looked at to make that work in something like WFIRST. There's going to be a down select, I think, in the next month between different technologies that have been brought forward. But all of these have the common capability of rendering as much as a part in 10 to the 9 contrast in your coronography, which is what it takes to go take a picture of an exoplanet, right? Because planets aren't shining on their own, they're just reflecting light, and they're right next door to this big bright thing called star, and we want to get rid of that. We want to throw all those photons away, but we want to keep the photons that are coming from the planet itself. And in magnitude space, if you choose to use those units, the kinds of planets you're going after are like 31st magnitude objects right next door to stars that are maybe 18th or 19th magnitude, right? So it's a big problem in terms of dynamic range, but it's doable. What it requires is exquisite control of your wavefront. And it means that the mirrors that you use have to be accurate and have no ripple in them to something like a part in lambda by 20, which is hard to do, but it's not impossible. And in fact, when you talk to mirror manufacturers, you find out that they're actually way capable of things that you didn't think they were in the past. And you ask them, why didn't you give us this kind of accuracy in the past? And they say, because you never asked us to. Because the way it works in industry, right, is they will keep grinding until they meet spec, and then they'll stop. And so if you said, actually, I'd rather have lambda by 20, please, because normally you ask for lambda by 8, right? And apparently they can do it. It just means turning the crank another week or two. And
Yeah, not that much longer, right?
it doesn't take that much longer, and it only represents another 20 to 30% of the cost of the mirror, which is dramatic, to say the least. So those are the kinds of approach. The other approach is external, right? The idea that here's the telescope, I'm looking at the bright light right up at the screen there, and I fly something essentially like a thumb to stick in the way. However, a thumb is the wrong shape. What you want is something that is actually the Fourier transform of a step function, and the thing looks like a sunflower.
That's right.
It has these weird pointy little petals, but if you want to do this in space, you need to fly one of these things about 100,000 meters away from your telescope, and it needs to be tens of meters across. And there's a group at JPL right now that's actually building a prototype one of these. So,
If you put $1 million laser on JWST, which we haven't done, but we could in the budget, then Northrop could, for $300 million, including the launch vehicle, launch 2 of these. They're 70,000 kilometers in front of JWST. So you know 2 months from now you're going to look at that exoplanet for, let's say, 2 weeks. You fly a sun shield over there, so it's right there with a centimeter precision, 70,000 kilometers away in altitude. You do your chronographic observation. That's not currently in the budget, but it could still be done. Yeah? Or you could build the next generation of these kinds of instruments to do just that.
but Roger touches on a couple of issues.
Yeah.
A, you've got to sit there for a long time, right? You're trying to find a 31st magnitude thing, and you're throwing away most of the light you're collecting, right? The other thing is, it's easy to just slew the telescope around to look at different objects. If you've got this second piece that has to fly along with you, it takes a long time to slew from object to object, so it limits the number of targets you can do this to.
So just to recap, Paul talked all about this beautiful concept, which could be done today. If somebody, government or industry, came up with $1 billion or so, you could launch this thing in 5 years. You know, that's the next perfect wide field Hubble. God forbid the day Hubble dies, we'll need. In the long-term future, you folks ought to build this. It's an 8 or 16 meter. This is not JWST, but it's, you know, with more mirrors, larger. It doesn't have to be built all on Earth and launch. You could build it next to the space station or somewhere in lower orbit with a robotic arm. Lay all these segments down, build them robotically, and then ship it out to altitude and do your thing. Once you have that 20 years from now, there's nothing that stops you for $300 million. This will be a many billion-dollar mission, probably 10 or 15 billion. To put over there 70,000 kilometers in front of it, a big sun shield, and do your exoplanet for you. A bargain discount, you can have your perfect current. Yeah? Compared to a $20 billion mission. You can't, you just have to plan it. So you guys go build it. Yeah? You want to see an Earth at the moon at 100 light years away? There's your toy. Yeah?
So we could do maybe one more question, and we have to wrap up.
Over there.
My question is actually for you. Do you have any of the galaxy merger simulation videos on you right now?
For the sake of time, I have a cheap version, and I'll let you browse my website that's listed in the references to do that. This is the extended version of my talk, so I'll get to. I've seen these beautiful mergers here. See, let me go to grab them. Where are they? Coming up here. All right. So we've seen some of this, and so if you imagine our Andromeda galaxy, I think I showed it during my talk, but I'll show it again to those guys. This is our own galaxy, South Mountain. That's the Andromeda. Turn all the lights in Phoenix off. That's the nearest galaxy, 2 million light, 2 million light years away from us. It's really close. It's actually, Hubble has shown, it's one of the very few galaxies, Hubble, the astronomer showed in the 1920s, that it's actually not moving away from us like freshman presenting, slowly colliding. It's blue shifting. Hubble, the telescope, the last 2 years showed that not only is it blue shifted towards us, it's going to hit us like a pancake, but it has no lateral motion, so it's actually going to pancake us in 5 billion years. This is what the sky will look like in 2, 3, 4, 5 million years. We no longer have a galaxy there. The galactic plane will be gone. There will be this ugly, giant elliptical sitting there with a supermassive black hole in the center, right? 5 billion years from now, you don't have to sell your real estate just. So I didn't really answer your question. This is not a movie, but there is a movie of that in the website. So search for this, Google it, Google this, and you will find it. Yeah, there's a whole movie of this. This was obviously done with simulations based on real data. But yes, we do have that, and there's a lot more on that. So how's that for a long answer? Yeah?
All right, let's thank our speakers one last time.
So we'll be around for a little longer in case you have any